in respect of reverse current is known as stability factor, and here we will calculate the stability factor in terms of beta and IB or IC. Okay, fine. So can I define the stability factor of fixed bias network? Here, okay, we were talking about how to find out the stability factor for fixed bias circuit. So we can call it here. We can recall that fixed bias circuit network equation. This was the first equation. This was the first equation. Okay, and minus BCC plus IBRB plus BB equals to 0. Okay, and this was the first equation, and this was the second equation. So here we need to, for finding the stability factor, we need to calculate this term del IV over del IC. So can I take that equation number second, equation number 2 from fixed bias network? The value of this stable. Can you do this exercise? Stability factor for each and every kind of biasing in the later sessions. Okay, so today we'll continue with the potential divider bias. Potential divider biasing is also known as self-biasing. Okay, self-biasing. And the network for this potential divider biasing, simply we are going to implement an amplifier. So we'll use common emitter configuration. Okay, and in common emitter configuration, this will be the potential drops plus minus BC across the collector to emitter terminal, and this will be plus minus BB. Okay, fine. Now I will connect this transistor into biasing network. For potential divider biasing, we do one kind of exercise. We use, this is fixed bias, okay? Till now, this is fixed bias. This is RC and this is R1. Now, in potential divider biasing, along with the fixed biasing network, we use emitter resistance RE and one resistance at this terminal. This is called R2, and this is input voltage, and here we collect the output voltage. That is fine. I think there is no issue. And this current is IC. This is voltage plus VCC. This current is IE. Okay, and one more thing here. For analysis of this circuit, we use Thevenin's theorem. Have you studied Thevenin's theorem?
Yes, sir.
Yes, sir.
Yes,
sir.
Yeah, similar kind of thing we utilize here for calculation of this different parameters related to this potential divider biasing of common emitter transistor. Okay, what we do generally for finding, we have to calculate the value of this resistance of VI. So let me make this circuit simpler. Circuit like that. R1, R2,
Yes, sir.
RC, RE plus VCC plus VCC. Again, I can make it more simple. VCC, this is RC, this is R1, this is R2, this is RE, and this is plus minus VCC. Can I redraw the circuit like that? Is there any problem?
Yes, sir.
Yes, this is very easy configuration. Okay, now we can sort it out, and this potential drop is VI. I don't think there is any problem to anyone. Okay, because these are simple wires and we can arrange these wires in our way, in which way we can see it very easy. Okay, fine. And then we can calculate the equivalent resistance first. Equivalent resistance. So I'll calculate the equivalent resistance of this network. We can remove the voltage source by short circuiting it. Okay, and from terminal side we can see the resistance R2, R1. And this resistance, this is called Thevenin's equivalent resistance. This will be R1 parallel to R2. And this will be R1, R2 on R1 plus R2. I don't think there is any problem. Is that fine?
Yes, sir.
Yes. And then we have to calculate the value of this voltage VI. How we'll calculate the value of this voltage? We can simply apply the potential divider network, or we can apply KCL, KVL, like we are having this network. Okay, this is VI. Fine, and this is R2, this is R1 plus minus BCC. So if I say this current I, okay, then in that case I can apply KVL and I can solve this minus BCC plus IR1 plus IR2 equals to 0. And in that case I'll find I equals to BCC over R1 plus R2. Fine. And now if we need to calculate this PI, so what will be VI? VI will be I into R2. Okay, and that I we can calculate it from our equation. This will be R1 plus R2 and it will be multiplied by R2. Okay, and this voltage is known as Thevenin's voltage. Thevenin's equivalent voltage. Now we can make an equivalent circuit of this whole network, and that equivalent circuit will be containing one Thevenin's voltage, and in series there will be Thevenin's equivalent resistance. It will be BTH. Okay, and here all load will be connected, and load is another part. Fine. I hope you understood. So we can make another equivalent circuit analysis for this analysis.
One-sided output. First, we will find one-sided output, and after that, we will find two-sided output. One-sided output.
Here PTH equals to BCC R2 upon R1 plus R2 and RTH equals to R1 R2 upon R1 plus. Is there any problem? I don't think there is any problem. Now this current is IC, this current I suppose this is IB and this is already IE. So can I apply KVL now? Yes. So in the first loop I can apply KVL minus BCC plus ICRC plus here it will be BCE plus minus and here it will be BBE. You remember that. And plus BCE plus IE RE goes to 0. This is equation number 1. And again, you can find the second equation by applying KVL at the input loop. Minus VTH plus IB RTH plus BVE plus IE and RE equals to 0. This is equation number 2. Is there any problem?
No, sir.
Yes.
Zero minus current following is to RC, then how much current is flow through RC? GM D by 2. So GM D by 2 into RC.
Potential divider by, and we can solve a numerical. We can solve a numerical using for this potential divider biasing, and here
And you know,
I'm taking a numerical.
we can also write equal to minus GM. And if I do also क्या लिख सकते हैं? Minus divided by
This one.
R plus R into R.
Determine calculation. Determine the bias E and IC for potential divider configuration. Okay, and configuration is given like
R5 equal to right here equal to minus theta minus R5 plus R. Now I'm assuming this is equation 2. Put the value of V from equation 1 into equation. These are the value of phi and equation 2 equation 1 into phi and equation 2. So साथ में क्या होगा RC. So you can write
and this value of VCC is given as 22 volt,
R5 plus RB
and this is 39 kilo ohm, and this is 3.9 kilo ohm. RC is given as 10 kilo ohm, and RE is given as 1.5 kilo ohm. Okay, and this is 10 picofarad. This is 10 microfarad. Here this is 50 microfarad. Okay, solve. So simply first draw the simple network of this circuit.
तो अब आप क्या करो एक्सपेंड करो इस इक्वेशन को तो अगर मैं इसको एक्सपेंड करूं
and beta is given as 100. Okay, and this is RTH. This is PTH. You see, I have removed all the capacitances. Here from this network, I have removed all the capacitance. Do you know what is the functioning of these capacitances? Though you don't know, yes. So these are known as coupling coefficient, coupling capacitors. coupling capacitors. Okay, coupling capacitors, and these are C1 input and CC not, and there is one emitter bypass capacitance, and this is denoted by CE. And specifically, this term is CE, this is CC not, this is CCI, coupling capacitor at input, and this is CCC not, and this is CE. And let me explain you. Like here, do you know this? Currently, we are performing DC analysis. We are having fixed voltage for as a power supply. We are applying fixed voltage. This is non-varying. But what happened in the case of AC analysis? In the case of DC analysis, the capacitive reactance is 1 upon omega C. And in case of DC, this capacitive reactance becomes infinity because capacitor offers no static charge, and this terms becomes this XC is infinity. This behaves as open circuited. Fine, all the capacitances behave as open circuit for DC analysis. For DC. Fine. In that case, if these are open circuited and we are performing the DC analysis, so these are open circuited. So in that case, we can remove this capacitor simply. Fine. And directly we will collect output here, and we will directly apply input here. Fine. And what is that? So these are called coupling capacitors, coupling input coupling capacitor and output coupling capacitor. What happens in the case of AC? Do you remember that filters? This was made up of R and C networks. So here R is already present and C is there. If we apply some AC signal in this amplifier, in that case, this capacitor behaves as a filter, and selective frequencies will be passed at the input as well as at the output. Undesired frequencies will be blocked from this capacitor because this is behaving as a filter. Is that clear to you?
Yes, sir.
Yes, and this is called emitter bypass capacitor. Sometimes what happens, there is heavy flow of current. This is across emitter resistance RE. If there is heavy current IE across this emitter terminal, in that case there is a chance, because this is combination of input current as well as collector current, and both currents are coming from supply. So there is a chance of flow of heavy current IE across this emitter terminal, and there is a chance of burning out of this transistor. And if there is a chance of burning out of this transistor, in that case, this will be a very difficult situation. And in bigger systems, we cannot afford this kind of exercise. So in that case, in bypass, we use one capacitor, emitter bypass. Generally, what happens if there is a flow of heavy current at the emitter terminal of transistor, then it does not follow that resistance. This capacitance, emitter capacitance, offers a low resistance path to that current. And we know that concept, current always follows the lowest resistance path. So in that case, this whole current does not passes through this RE. This is bypass by a emitter capacitor. So that's why this is called emitter bypass capacitor. Fine. I hope you understood. And this is resistance RE. This is 1.5 kilo. This is simple network, and we'll find VTH. This is BCC R2 upon R1 plus R2, and VTH becomes 22, and R2, what was that? R2 3.9 into 10 raised to the power 3, and 3.9 plus 39 into 10 raised to the power 3. And VTH, you can calculate. I think you can calculate the value of VTH. All the participants are requested to keep themselves on mute.
Then you can play with this phone.
It will be, I think, it will be something. You can calculate 2 volt. Fine. And
Yes, sir.
then
2 volt will be the answer.
yes, and then you can calculate the value of Thevenin's equivalent resistance. It will be R1 R2 upon R1 plus R2, and it will be 339 plus 3.9 upon multiplied by 39 plus 3.9 into 10 raised to the power 3 ohm. And RTH you can calculate from here. It will be 3.55 kilo ohm. Okay, now you can put this value of VTH and RTH, and you can apply one equations, KVL equations at the input and output loop simultaneously. So what will be that? Let me explain. So it will be plus VCC minus 22 plus, if I apply this, if I consider this current is IC and this current is IE and this current is IP, and it will be IC into 10 kilo ohm, 10 into 10 raised to the power 3, and plus VCE, 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 and plus IE into 1.5 into 10 raised to the power 3 goes to 0. This is equation number 1. And you can apply the KVL at the input loop, then it will be minus VTH 2 volt plus IB into 3.55 into 10 raised to the power 3 plus, and one voltage will be E, and this voltage value will be 0.7 because it is not given, and we consider that transistor is working in active region. Fine, and here it will be okay 0.7, then plus I E RE equals to an RE value. You can put the value of RE and it will become 0. And IE, again you can keep this in your brain. I equals to IB plus IC. You can put this value here. Now you are having very few variables and you can calculate the value of, and one more thing you can have to remember, IC equals to beta IB and IC not equals to 0 in the case of common emitter configuration. You can put this all value in equation number 2. You can calculate the value of IB. Then you can put this value of IB here in equation number 1. You can calculate the value of this BCE, and from this relation you can calculate the value of IC, and this is required to calculate. I don't think there is any problem. If some problem in all these calculations, so you are please requested to just explain your thing right now. Once you are stuck in these problems, it will be very hectic work to solve the numericals for you. So please, right now, you just tell me your problems.
Sir, in such type of questions, whenever there is a capacitor, we will a short circuit that.
Yes.
Okay, sir.
Not me, open circuit. We will remove those capacitors.
Okay, yes, sir.
Okay. Let me do other exercises and next type. Yes, tell me.
Sir, if we do this type of problems with the help of mesh analysis, will it become lengthy or means?
What is mesh analysis? This is simply KVL, na?
Yes, sir.
Yes, that is simple KVL. Mesh analysis means simple KVL analysis.
Yes, sir. Yes, sir.
So that's what we are applying. We are using mesh analysis only.
Okay.
Collector to base bias. collector to base bias. Okay, let me explain the circuit. Here is bias. When we take, this is also called emitter feedback, collect feedback bias, collector feedback bias. Collector feedback bias. What is the meaning of this word feedback? I'll explain. This is RC and this is plus VCC. This is RB. Okay, and this current IB, and this is IE, and this is RE. And as usual, this voltage drop across this output terminal. This is VCE plus minus, and this may be VBE plus by. And this is also known as feedback loop. Excuse me for a second. What is the meaning of this word feedback? Let me explain. What is the meaning of this word feedback? Generally, here in this configuration of amplifier, we take output here. This is load resistance. Okay, we collect output here at the collector terminal. Okay, after resistance, collector resistance. So what is happening at this point? We are collecting output. So what we do generally, we take some amount of current. We take a current from that output terminal, and we apply that current to input of the device. Understood? This is like suppose I am having one system, and here if this is we are collecting output at this point and we are having this input. We take current from output and we apply it at input. Okay, and this is called feedback. So this kind of structure is you are seeing here. This kind of a structure is this. So you are collecting some current from the output terminal and you are applying it to the input. So this is called feedback. Okay, fine. And collector to base. And the meaning of this word collector to base. I hope you are able to understand the meaning of this collector to base. From collector to base of the transistor. Okay, so now we will apply some KVL equations. Simply plus VCC. If I say this is if I consider this is current IP, IC, and IP, in that case plus VCC minus VCC. Sorry. This IC, this is IE already mentioned, minus VCC plus ICRC plus VCE plus IERE equals to 0. This is equation number 1. At output loop, at input loop you can apply similar amount of current minus VCC plus ICRC plus IBRB at this output loop. IBRB plus VBE, okay, plus IERE equals to 0. This is equation number 2. I don't think there is any problem in writing this equation. So directly I am going to solve a numerical problem. It will be very easy for you to understand. Determine VCE and ICQ. Fine. And network is given like 1.2 kilo ohms. This is 4.7 kilo ohm, and this is 10 volt. And here we will apply one resistance at the input terminal. It will be 250 kilo ohm. And here this is the capacitor connected. This is 10 microfarad, and this is input terminal. And one capacitor is connected here at the output terminal, and this is 10 microfarad, and beta is given like 90. This is plus 10. Can you solve this numerical by yourself?
Yes, sir. Yes, sir. We try.
Can you not make it close? Remove capacitances. Because we are performing DC analysis. Okay, so we'll remove this, we'll remove this. So first we'll make it simpler. Oh, you can only solve if this is closed loop. This is not a problem exactly. Okay, I have removed capacitors. This is RE, this is RC. Learn this, how I am able to remove this plus PCC. This is plus terminal, and definitely if this side is having plus terminal, then this side will be having negative terminal. Am I clear? And if I represent this in terms of battery, then big terminal of will be at this side, and small terminal will be at this side, and definitely this will be connected to ground. Okay.
Yes, sir.
Okay, fine. So now, can you see the closed loops here?
Yes, sir.
Yes. Now make it more simpler. Plus minus PCC, RB, RC, RE. Okay.
Yes, sir.
Now I know this is VCE plus minus, and I know this is VE plus minus. Okay. So again, I can reconfigure this network. Just see this. Input loop. Okay, and I can make output loop as well. Mr. Raji,
Yes, sir.
now do you feel any problem in this?
No, sir.
This is output loop, this is input loop. You can directly apply KVL and you can find all kind of. Here this is current IC and you can make this terminal open, and here this is current IB and here this current is IE, and directly this current is IC and this current is IE. This is output loop. This is simplest version, whatever I can explain. So I think now I can apply KVL and KCL and I can solve this numerical, and beta is given as 90. I don't think there is any problem now. Is that fine?
Yes, sir.
Yes. And biasing. So okay, before going on that, I would like to give you another numerical problem. And can anyone solve this problem? This is very good, because this capacitor will be removed for DC analysis and everything will be simpler, like previous collector to base bias. Okay, but one thing I want to do, like if I do one exercise, if I modify this circuit and I do one thing, I apply one battery here, plus minus 10 volt. Now tell me, can you solve this numerical problem? Oh, okay. You try to take the screenshot of this numerical and try to solve this problem. In that case, you can consider yourself excellent person. Okay.
So value of beta?
Beta is given like 75. Okay, you try to solve this numerical problem. List down bias stability factor. Okay, we will analyze that. Okay, BJT as an amplifier, low frequency small signal model, common modulator amplifier with and without feedback. Okay, CE amplifier. This potential divider bias with capacitances and all the things. This is also known as RC coupled amplifier. Okay, so this portion is approximately finished. I'll re-explain, a little bit amount is remaining. so you can understand this in easy way. Multi-stage amplifier, BJT switch, cutoff and saturation mode. Cutoff and saturation, BJT switch you already studied. Cutoff and saturation mode you studied. Okay, how it is being utilized in switch, I'll explain. This is 5 minute process. Multi-stage amplifier. There are three kind of multi-stage amplifier: Darlington pair and cascade amplifier. This will take 5 to 10 minutes. So most probably tomorrow we'll finish our syllabus of second unit, and from the next lecture we'll try to finish that. We'll try to study at that field effect transistor from next week onwards. Fine, your second unit is approximately finished. So you please keep doing hard work specifically for this PJT. And you one thing, this is my suggestion for you guys. If you understand the operation of BJT and diode properly, then solving the problems related to other subjects throughout your electronics engineering will be very easy for you guys. Otherwise, you will stuck in the small problems related to your whole AC, electronics, and communication engineering department. So to do self very hard and perform all the numericals, perform all the analysis by yourself. If you feel any difficulty, please share it with me. Fine.
Unintentionally. So we obtain the real power. Real power was found to be root 3 VL IL cos phi. So this can be expressed in watt or kilowatt if you can put 10 to the power minus 3, whereas phi is the phase angle between the VL and IL. And similarly the reactive power, total reactive power and the total real power. Reactive power was found to be root 3 times VL IL sin phi. So if you had written the unit of this by watt, so please rectify it as VAR, it is volt ampere reactive. And then so this we denoted it as P and this we denoted it as Q, and the total apparent power S was found to be root of P square plus Q square, which was root 3 VL into IL. So this was volt ampere. So kindly note this if you had written by mistake as watt. So today we'll try to complete the relationship between line and phase voltages for delta connection. In the last class we did it for star connection. So in this case we will try to obtain the line and the relation between line and phase quantities for delta connection. And this will be B. So as you know here, the neutral point is not available as it was for the star connected network. So here the neutral point is not available directly. Now, if you can note this as R, this as B, and this as Y, so that the voltages that I am going to mention will make sense to you. Now, when I say line voltage between VR, the line VR and Y, so VRY, this will be same as the phase voltage as you see here in the delta connection. Okay, so this thing you can note that this line voltage, let's say the voltage between R and Y, will be same as the voltage in this particular phase. Okay, so the line and the phase voltages are identical. In the same way, if you can look at the voltage between Y and B, so this will be same as the voltage in this phase. Okay. So the line and the corresponding phase voltages are identical. We denote it as V. But if you look at the phase angle, they will be 120 degree apart. Let's say this will be 0 degree, minus 120 degree, and then minus 240 degree, or you can also write it as plus 120 degree, whatever. Now, if you want to find IR, you can very well relate this current IR with IBR and IRY. So, which means that the current in each line, so this is the line, so the current in each line is the difference between the currents in the two the difference between the two phase currents. Okay, so this will be the vector difference between these two phase currents, that is IR will be equal to, let's say, IBR, this is the incoming current at this point, minus IRY. So I don't know why there is, and this IY will be nothing but IRY minus IYB. Minus IBR. Here you must understand that all these are vector quantities, which means that to find IR, I have to draw the vector of IBR and then minus IRY. So then I have to simply add IBR with minus IRY. So IRY is nothing but if I can change the direction of IRY, I will get minus IRY. So just as we did in the previous case. So which means that your IR will be IBR plus minus IRY. Try to reshare the screen.